Hello, this is the second of the three lectures on chapter one, which is measurement for H2O physics. Okay, so a bit of recap from the previous lecture. So in physics, the data is very important when you do experiments. So when you do experiment, you need to take measurements. And the thing is that measurements are not perfect. Okay, so because there are errors, so when you measure something, there are errors that causes uncertainty. So we need to take that into consideration. So the previous lecture, we talked about two kinds of errors, random errors and systematic error. Okay, it is not difficult, but it is important. Important because you see this asked all the time in the A-level exams. So as mentioned previously, our convention in our lecture notes is that anything that is boxed up, okay, such as this, okay, it means that it's very important. It's asked often. You need to know how to be able to write this. What is a random error? Random error is an error which causes measurements to be sometimes larger than the true value and sometimes smaller than the true value. Okay, so it's not good enough that you read, you understand. No, you have to practice writing it out yourself without referring. Once you can do that, you have passed that mark. Okay, and then you can move on. Okay, so that is random error. You see, this is the true value here. So if the error causes the measurement to be sometimes larger, which is on the right, sometimes smaller, which is on the left, then that error is a random error. So for systematic error, it is an error which causes measurement to be either always larger than the true value, which is in this case, or always smaller than true value, which is in this case. Okay, then that is a systematic error. So in the definition of systematic error, please take note that the word always have to appear two times, because if the word always appear only one time, then the write-up is no different from that of a random error. Okay, because if you say it's either always larger or smaller than true value, means it's larger or smaller, which is random. So you must say it's always larger than true value or always smaller than true value. I hope by now you can see the difference. But most importantly, please note that in this write-up, you have to say that the systematic error is an error which causes the measurement. So if all you say that systematic error is either always larger than true value or always smaller than true value, that's wrong, because the error, but you must say error which causes the measurement, what it does to the measurement. Okay, so this is a recap from yesterday's one, the previous lecture, and also you also need to know the distinction between precision and accuracy. Okay, so precision refers to the spread, the scatter of repeated measurement of the same quantity. Accuracy refers to the agreement between the results of your measurement and the true value. Okay, so in terms of definition, these are the four things that is often asked for this chapter. What is random error? What is systematic error? What is precision? What is accuracy? So you have to know these four, and they are all boxed up. Okay, so we can now move on. This was, we went through this. We went through work example 10, 11. We went through work example 12. So now this is the new part. Estimating maximum possible error in a single measurement. This is very important for practical. So the theory here, you'll be your knowledge about this will be tested both in practical and also in theory paper. So you need to know. Okay. Now, the random error in any particular measurement is an estimate only, and it has to be reasonable. So the random error can only be given to one significant figure. So it is important. Maximum possible random error is normally estimated to half the smallest division. Okay, so these two are very important, but we'll illustrate this using this work example here below. Work example 13. Estimate the error in the thermometer reading below. Okay, write down the reading of the temperature to the correct degree of precision. Okay, so assume that there's no systematic error here. Now, so let's say this is the thermometer's uh, scale that you have here, and then this is the level of the bulb. Okay, so what is the smallest division? The smallest division is 1 degree. Okay, as you can see, you look at the scale, I have 90 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. So each division, each smaller division for this scale is 1 degree. So this is like a typical mercury in glass thermometer. This is different from clinical thermometer. Clinical thermometer, you can measure the smallest division is 0.1 degrees Celsius. So this is a typical mercury in glass thermometer. So based on this scale, you can see that the smallest division is 1 degree Celsius. Therefore, the error, okay, the error as seen from point 2, okay, is half the division. So the error will be written to be 0.5 degrees Celsius. Why? Because let's look at this. Let's make the scale bigger. Okay, let's call this 1, 2, 3, 4. Now, if you look at the instrument, if let's say the thing falls on this, you'll say that, oh, it's value 2. If it's here, you say it's value 3. But what if it's here? Well, I'll say that it's 2.5. Okay, so because you can see that this is around the middle, so this is 2.5. But what if it is slightly to the left of this 2.5, or what if it's slightly to the right of this 2.5? So how precise can you go? But your precision is only 1 division. So what I'm trying to tell you is that if the precision, the smallest division is only 1 degrees, then you can read it accurate only to half the smallest division, which is 0.5. Okay, so in this case, if you write 2.13, it is not possible. How can you know it's 2.13? On what grounds? But if you say it's 2.0, 3.0, 2.5, you can see. Because, okay, let's draw the scale again. So if let's say the arrow is here, and this is 1, 2, 3, 4, okay, so this one I can say that it is so what is this reading here? I can say that it is maybe, let me see, 1.5. Okay, so it's 1.5 because it's closer to the middle than to the side. If I say it's 2.0, it's wrong. If I say it's 1.0, it's wrong, but it's closer to 1.5. But I cannot say it's 1.6. I cannot say it's 1.7. I cannot say it's 1.52 because there is no scale in this case that can help me read to that precision. Clear? So once again, you see what is the smallest division, and your reading will be, the error will be accurate to half the smallest division, 0.5 degrees. So this should be written as you can see, this is 96.5, 96.5 plus minus the error 0.5 degrees Celsius. So this is how I write this one. And most importantly, the precision of the error, which is supposed to be 1 significant figure, the precision of the error must be the same as the precision of the reading. So my error, the precision is 1 decimal place. My reading, the precision is 1 decimal place. Okay? Okay, let's move on. Later, when you see more examples, you'll be able to understand this better. Okay, now, please ignore this one. Okay, now let's measure the length of this ruler. Okay, so first of all, this is about 1.8. Okay, the unit is cm. Now, what is the error? Okay, the smallest division, as you can see, is 0.1 cm. Okay, the smallest division, as you can see, is 0.1 cm because the big scale is 1, so each of these small division is 0.1 cm. Okay, so the error would be half the smallest division. So the error, which is half the smallest division, will be 0.05 cm. Okay, but this is different from the thermometer. If you look at the thermometer, when you want to see what is the temperature, you take only one reading, this one. Okay, but here, okay, here for this ruler, if you want to know what's the length, you take 2 readings because you take 1 reading here and 1 reading there. Okay, so 2 readings. So because you take 2 readings, the error should be added up. So the error or the uncertainty should be 1 division because it's half division plus half division. Okay, half division plus half division equals to 1 division. Therefore, in this case, the error is not 0.05, the error is 0.1 cm. Okay, so therefore, the reading is 1.8 cm, so it has to be written like that. So the error is 1 division because it's half plus half. The error is 1 division, so it's 0.1 cm. The reading is 1.8, so it will be written like that, 1.8 plus minus 0.1. Same precision, which is 1 dp, and same precision there. Okay, so I hope that's fine. Let me pause this. Okay, so now, so let's continue. Okay, so what are the kind of things that they'll ask you to calculate? So, or to determine actual fractional percentage error. So you need to know this. Actual error, or sometimes known as absolute error, is denoted like that. Okay, so if let's say the length, uh, the quantity is a length, so the absolute error, actual error will be written in this form, delta L. Okay, and remember it has to be one significant figure. Now, fractional error will be delta L over L. Okay, delta L over L, and it has to be a number at the end. Percentage error is delta L over L multiplied by 100%. It has to be a number at the end. Now, for fractional error and percentage error, it is permissible to write up to 2SF. Only for fractional error and percentage error is permissible to write up to 2SF, two significant figure. Okay, but for absolute error or actual error, it has to be one significant figure. So L can be written in this manner, or maybe even like that, but this is very rare. Okay, normally you write it in the same form. So please look at this. What I've mentioned is there. Okay, so the next part is quite self-explanatory. Uh, so ruler can measure up to 1 mm. Vernier calipers can measure up to 0.1 mm. Micrometer screw gauge can measure up to 0.01 mm. So the reading have to be written accordingly. Like for example, ruler. If you write a measurement that's used using ruler to do, because a ruler can measure until let me see, if the ruler can be measured until 1 mm, if it is 1 cm, then it must be written to 0.010 meter. Okay, because ruler can be, the precision is 0.001 meter, which is 1 mm. So the reading, even if you know it's 1 cm, you cannot just write it as 0.01 meter. It has to be written to be 0.010 meter, the same precision. So 3 dp, 3 dp. Okay, so this is, we put this here, but as you go on, if you do experiment, tutorial, you'll be able to grasp all this. All these are very important, it's heavily tested, and but it's not that difficult actually, you know that. Okay, so it's mentioned as per that important. Okay, now let's look at this. So how do we write the values now? So in this case, the measurement is this. Okay, the measurement of this pressure is written in this manner. So is it correct or wrong? Okay, let's see. 929.345 plus minus 0.012. So is it written correctly? Now it is wrong. Okay, why? It is because this is the absolute error. It has to be to 1 SF. After this become 1 SF, this becomes 0.01, then this is 2 decimal place, then this one will have to be written to 2 decimal place. Okay, so the correct way of writing this should be 929.35 plus minus 0.01. Okay, that is the correct way of writing the first one. So the second one, now this is 1 dp, that is fine. 1 SF, sorry, this is 1 SF. So after it's written 1 SF, it become 1 dp. So this one had to be written to 1 dp. Same thing, 929.35 plus minus 0.01. Okay, so this is correct. Okay, so this part is not filled in your lecture note, so please fill it in. Now, for this case, the absolute error is 10. Okay, the absolute error is 10. So this part is 10, which is one significant figure. So that's fine. So this one you have to be same precision. You have to rewrite this until it's in the tens. So the correct way of writing this is 930 plus minus 10. Okay, because this is 1 SF, and after writing 1 SF is in the tens. So this one, the reading must also be written the same precision, which is in the tens. So you have to round off to the nearest 10, which is 930. Okay. Now this one is correct. Please look at this. 1 SF, so it's 2 dp, and the reading is 2 dp. That's fine. Okay. So these three are not in your lecture notes, so please fill it in. Okay, so work example 16 is quite straightforward. A student measures the diameter of a cylindrical wooden pencil with a meter rule. How could he get the highest precision? So precision normally depends on the instrument. Okay, precision depends on the instrument. If you use a ruler to measure something, you can only measure to the precision of 1 millimeter. But micrometer screw gauge, okay, micrometer screw gauge, you can measure it to 0.01 mm. So that is the highest precision. Okay, so the answer is A. Now they say take average reading, average. If you take average reading, it's just to get higher accuracy, not higher precision. Okay, so once again, precision normally depends on the instrument. So the answer lies in the instrument. Okay, this is very important, okay, because this refers to the rules in giving your answers in the theory paper. Okay, so as you know, physics, there are 20 chapters, 4 papers. Paper 1 is multiple choice, so that's fine. Paper 2, 3, 4 are all theory paper where you have to present your answer to the correct SF. So whatever chapter that is, okay, whatever chapter that is, if your answer is not presented to the correct significant figure, you will be penalized 1 mark. Okay, so this is very important. Now, how should you present your answer? The thing is, uh, I'll just illustrate using this example here. So we have a formula, voltage equals to power over current. Okay, you've learned this in secondary school. Voltage equals to power over current. So you're supposed to calculate the voltage or the potential difference. What is the values given to you? Now, power 2.005, current 1.7. Okay, so let's look at this. 2.005 is 4SF. 1.7 is 2SF. So the rule is that your final answer, you have to look at what is the least significant. Okay, what's the least significant? So in this case, the least significant is this one. 2SF is of course less significant than 4SF. So the least significant data of all the data you're given, the least significant data is this 1.7 ampere, which is 2SF. So your final answer must be equal to the lowest significant figure or lowest significant figure plus 1. So in this case, your answer must be 2SF or 3SF. Okay, clear? 2SF or 3SF. If you have written your answer to 4SF, you will lose 1 mark. Okay, you'll be given full marks for that question based on the correct answer. After that, you'll get 1 mark deducted. Okay, that's how it is. Okay, so that is for equation, that is multiplication and division. For addition and subtraction, you follow the lowest significant. Okay, like for example, in this case, this plus this, goodness gracious me. So 4 dp plus 2 dp, your final answer is 2 dp. Okay, So these are the rules. Now, this will be assessed in paper 2, 3, 4, especially practical. Okay, especially in paper 4, where the penalty is more severe, but also in paper 2 and 3. So even if your answer is correct, but you'll get full marks for that question, and then you'll get 1 mark uh, deducted for wrong significant figure. Okay, so this is example. So one same SF or one more is acceptable. One less, two more, you'll get marks deducted. Okay, so this is starting to become new and more complicated. So this is the error computation. Okay, so this is normally a structured question, 2 or 3 marks. It appears almost every year, but it's not that difficult. You should be able to do it. Just follow the rules. Okay, let's look at equations that is addition and subtraction. Okay, so now have a look at this. Uh, okay, just remember this principle about error. You only add errors, you do not subtract errors. Okay, you only add errors because the each operation has an error. The more operations there are, the more error there is. Error cannot be subtracted. Just remember this principle. So if you look at this, if the if the quantity that you measure is A and B, and you say that I want to find S, the formula for S is A plus B. Okay, so the error for S will be equal to the error of A plus error of B. So this is very straightforward. Okay, but if the equation is C minus D, the error, I mean Q equals to C minus D, the error for Q is still error of C plus error of D. So this is very important. You need to note error of C plus error of D, because you only add error. You cannot subtract error. Clear? Now, so in this case, if the formula is 3p minus 2q, then the error of R will be 3p, 3 delta p plus 2 delta q. So instead of negative, become a plus. If it's a plus, it stays at a plus. Okay, so hope you understand that. Now, this example 18, this is important. A student attempts to measure the diameter of a steel ball by using a meter rule to measure 4 similar balls in a row. Okay, so what is the diameter of a steel ball together with its associated uncertainty? So what is the diameter of a steel ball? Okay, so you put 4 together, then you have to divide by 4. Okay, but first of all, look at the associated error first. Okay, now this is a Cambridge question, but a lot of people will get this one wrong because they assume that, oh, it's a meter rule, so the smallest division is 0.1 cm, but sometimes it's not like that. Look at the scale that's been given to you. Look at this. Each division is not 1 mm. Each division is 2 mm. As you can see, like 5, 6, and in between there's only so between 5 and 6 there are 5 divisions. So each division is 0.2 cm. Okay, so you need to know that. Okay, so what is the reading? 5 minus 1 will be 4.0 cm. Okay, and then what is the error? Because you take so half the division will be, so one division is 0.2 cm, half the division will be 0.1 cm, but because you take 2 readings, you take a reading here, you take a reading there, so it becomes 0.1 back to 0.2 cm. Okay, so the error is, remember the error is half division plus half division equal to 1 division. So 1 division is 0.2 cm. But you have to divide by 4 because there are 4 there are 4 diameters here. So you want the diameter of 1 only. So you divide by 4. So you get 1.0 plus minus divided by 4, 0.05. But they have to be the same precision, so this become 1.00 plus minus 0.05 cm. So this is how you write it. Okay, so the full working is here. Okay, so the full working is here. I believe this part of your notes is blank, so please copy this down. So the associated error is 1 division because it's half plus half. So 1 division is equals to 0.2 cm in this case. So the reading is 5 minus 1 equals to 4. But we only want 1, so that divided by 4. So you get 1.00 plus 0.05. 2 dp, 2 dp. Okay, full working is here. Now, why is this, the following question is, why is this a better method than if you just measure one using one ball? You know, you always like take more, you divide out, so you think you have a more accurate reading. But why? The reason is this. Look at this. Look at this. 0.05, which is an error, the reading is 1.00. So it means that the percentage error here is 5%. Okay, the percentage error here is 5%. If you do it this way, the percentage error is 5%. But if you measure using just one ball, then the reading will be like that. And the percentage error is 20%. So that is why if you have more and then you divide out, you have a lower percentage error. So that would be a more accurate reading. Okay, so this is a more accurate way, and the reason is the percentage error is smaller. Okay, so the above are for equations where is addition and subtraction. So now let's look at what if the equation is multiplication and division. So if the formula is multiplication, let's say v equals to a times b. So how then do you calculate delta v, the associated error? So it's a different way of calculating. So the first thing you must do is that you have to make v the subject of the formula. So in this case, v equals to 3ab. V is the subject of the formula, so that's fine. And then you must then express it into fractional error. Okay, you must express this equation into fractional error. So delta v over b equals to delta a over a plus delta b over b. Okay, clear? And if let's say it's a division, it's the same thing. So express this in terms of fractional error. D equals to m over 4 pi v. So delta d over d equals to delta m over m plus delta v over v. Then once you substitute all this in, you substitute the value of b, you can calculate the value of delta v. In this case, you substitute the value of d, you can calculate the value of delta d. Okay? You may then ask, what happened to 3? What happened to 4 and pi? They disappear. Why do they disappear? Well, they disappear because 3 is not measured, pi is not measured, 4 is not measured. There is no error associated to it. Okay, there's no error associated to the number 3, 4, or pi. So that one disappears. That's why the equation is like that. What if there's a square here? Okay, in this case, look, pi r d square over 4l. So it is written in this form. Delta rho over rho equals to delta r over r plus 2 delta d over d plus delta l over l. Okay? So if you see a power 2, then you multiply the error by 2. But why? Because technically, this can be written as, because technically, okay, let's write it up on top. Rho equals to pi r d square over 4l. Now, basically, this can be written as delta rho over rho equals to delta r over r, because d equals to d times d, right? So I do it twice, delta d over d plus delta d over d plus delta l over l. So delta d over d plus delta d over d is equals to 2 delta d over d. Okay, so that's why if there's a power 2 down there, you just bring the 2 down. Okay, instead of writing out delta t over d plus delta t over d, it's simply 2 delta t over t. Yeah, so that's that. So remember things like 3 and pi has no error associated to it, so ignore it. So example 20, this is the equation. Q equals to 3ab squared over square root c. So the percentage errors of A, B, C are all given. So what is the percentage error in Q? So the first thing you see, this is not a addition subtraction formula. This is not an addition subtraction formula. This is a multiplication division formula. So if it's a multiplication division formula, you must first thing express the thing in terms of fractional error. It is written here. Okay, delta Q over Q equals delta A over A plus 2 delta B over B. Why 2? Because it's square. And then plus half delta C over C. Why half? Because it's square root. And then you substitute the values in. They say A is 1%. So 1% is just 1 because you do everything in terms of percentage. So 1 plus 2 times 3 plus half times 1. So no, half times 2, sorry. So finally, you get 8%. Okay, so this is how it's done. This will be self-explanatory. Next thing, the acceleration of free fall g is calculated using the formula g equals to 4 pi square L over t square. Okay, where L is the length measured in that manner. So this is the value given for L. Value of G is measured. So in this case, it's measured. So you have to include the uncertainty. Find the percentage uncertainty in the calculated value of T. Okay, so as mentioned earlier, look at the formula. What is this formula? This formula is the multiplication division type. So you must express it in terms of fractional error. But first, you must make what you're interested in the subject of the formula. Find the percentage uncertainty in the calculated value of t. So the first thing is play around the equation such that t is the subject of the formula. Later, I'll show you why that's so important. And really, that is so important. You don't do that, you'll get your answer wrong. Okay, so t equals to this. So delta t over t equals to half delta L over L. Why half? Because it's square root plus half delta G over G. Why half? Is because it's square root. Then this is the square root. Ignore the 4 pi square because 4 and pi square has no error. So what is delta L over L? Since L is 20.0 plus minus 0.1, so delta L is 0.1. L is 20.0. Okay. What about delta G over G? They say the percentage error is 2% already, right? So this is 0.02. So that's it. Delta T over T equals to 0.013. So the percentage error in T will be 0.013 times 100% gives you 1.3%. Okay, so that's that. Now, this is a special case. Okay, this is a special case. Work example 22. This is a 2012 question. The equation connecting the object distance u, image distance v, and focal length f for a lens is that. So that is the equation. A student measures values of u and v with the associated uncertainty. Okay, what is uncertainty in this value? Now, so let's assume that you are using the rules that you were shown earlier. So what is this? Is this addition, subtraction formula, or is it a multiplication, division? Okay, so let's rearrange the formula to this form. Okay, f equals to uv over u plus v. So this will make this a multiplication division formula where u multiplied by v over u plus v. So you consider u plus v as one term. So you write down in terms of fractional error. So delta f over f equals to delta u over u plus delta v over v plus delta u plus v over u plus v. And then you substitute everything inside. You'll find that the answer is wrong. Okay? You'll find the answer is wrong. 4.68, it does not match any of these answers, any of the 4 choices here. Okay, you'll find that it does not match. So this is wrong. So now, the thing is you have to recognize that the previous rule cannot be used in this case. Okay, it cannot be used in this case because u plus v and uv, okay, are not um, independent, are not mutually independent because they're mutually dependent. So the numerator is uv, the denominator is u plus v, and they're dependent on each other. When this v change of, I mean, when this v change, the top will change, the bottom will also change. So they are not mutually independent. So this method does not work. Okay, so to do that kind of situation, you have to use rule 3. For equations that involve terms which are dependent, okay, like in this case, like mentioned just now, if I rearrange the term, then the top is uv, the bottom is uv, they are linked, which means that any changes to the top will also affect the change in the bottom, the numerator and denominator. So for such cases, you cannot use rule 1 and 2, you must use a new thing called rule 3. And rule 3 is to calculate this way: maximum error. Put in the largest possible value, put in the smallest possible value, and then you subtract and divide by 2. Okay? So F max, 1 over U max plus 1 over B max, the largest possible value. Okay? And then you get 42.11. F min is 1 over U min plus 1 over V min, and then the smallest possible value is 37.87. So you take the largest minus the smallest, divide by 2, you get 2.1, and this is the answer. Okay, so most of the time, you are required to solve questions using rule 1 and rule 2. That's the more unique one. But rule 3 is the new one that's been coming out recently. Okay, so you have to be aware. So if the equation is like that, A equals to BC over C plus D, this is not, the numerator and the denominator are not mutually independent. So you cannot use rule 1 and rule 2, you have to use rule 3, and rule 3 is using this, the maximum error method. Take the maximum possible value minus the minimum possible value and halve it. Okay, and you should be able to get the answer. So we have this part called, in our lecture notes for every chapter, called the work example with visible thinking. Now, what do we do here is that we try to put questions which are slightly more difficult, okay, and hope that you will try it, and then we'll give the answers with full explanation, okay, explanation in which we teach you how to think about it, and then what are the possible errors that students normally make. Okay, so in this case, let's look at this. An experiment uses the following equation to calculate the resistivity of copper, which is rho, and this is the equation. So the rest were all measured: the diameter, the length, the resistance. So calculate the resistivity and write it together with the uncertainty. Okay, so that means you write the value of rho in this form. So what's the first thing? Let's look at the equation. This is a multiplication division type. So the first thing to do is to express the equation in terms of, that's not the first thing to do. First thing to do is you have to make rho the subject of the formula. Okay, because they're asking to find resistivity, so make rho the subject of the formula. After you make rho the subject of the formula, express the formula of rho in terms of fractional error. Okay, and then you substitute all these values inside. So let's jump straight into the answer. Now, so this is it. Okay, it's not going to hang, is it? Okay, here we go. So rho is now equals to r pi d square over 4l. So delta rho over rho equals to delta r over r plus 2 delta d over d plus delta l over l. Okay. Now, you substitute in the value because they give you all the values. So like resistance, they tell you that the resistance value is 0.1 plus minus 0.01. So the fractional error should be 0.1 over 0.01. So you put all these things inside. you know what the value of rho based on your previous calculation. You calculate inside, you have delta rho. Okay, so rho plus delta rho equals to this. Okay, so as you can see, your delta rho is 0.338 times 10 to the power minus 8, but it has to be written to one significant figure, so it becomes 0.3. But then your rho, you have to write it to the same dp. 0.3 is 1 dp, so 1.7 is 1 dp if it's to the same power, 10 to the power minus 8, 10 to the power minus 8. So that's how to do it. Now, let's look at some of the things to be very careful about when doing this question. I mean, it's not that difficult in terms of just following the rule and applying, but there are potential offside trap. Okay, if you are not careful, you'll make careless mistakes. Number one, you calculate the value of rho, check out the units. You want your rho finally to be of SI units, ohm, meter. So please, when all the data you fill in, it has to be in SI unit. Okay, so which means that for resistance, it has to be ohm. For the diameter, it has to be in terms of meter. If they give you the values in terms of millimeter, you have to convert to meter. The value of length should be in terms of meter. If they give you the value in terms of centimeter, you have to convert to meter. Okay, so substitution into equation, everything has to be in terms of the SI unit. If the final answer required is SI unit. Okay, that's number one. But having said that, when you substitute into this fractional error part, do you need to convert to SI unit? You don't need, because the conversion will cancel out numerator and denominator. So you don't have to. Okay. So yeah, so you just leave it as it is. Even if it's in cm over cm, it gives you the same fractional error. Over it gives you the same fractional error as if it's meters over meters. Okay, clear? Now, then the final answer, it can be written in, if you put 10 to the power minus 8, so it's 1.7 plus minus 0.3. If you put 10 to the power minus 9, so it's 17 plus minus 3. So this is fine because 3 is the same precision. 3 is the ones, 17 is also to the nearest ones. Okay, so the thought process is like that. You see this kind of question, first thing you ask yourself, if the equation such that the required quantity is the subject of the formula, if it's not, you need to rearrange it. So in this case, you need to rearrange it because the equation did not put rho as the subject of formula, so you have to make rho the subject of the formula. Is it a multiplication division or addition subtraction? If it's multiplication division, you have to form the fractional uncertainty equation. The absolute uncertainty must be 1 SF, the required quantity must be same precision. Now, for this question, what a lot of people, what some students may make the mistake is this one. Okay, so remember, every time we put on all this work example, we're trying to show you all the various possible examples, various possible questions that can be asked, and also showcase to you what are some of the common mistakes. This one, what happens if you did not? Okay, what happens if you did not make rho the subject of the formula? So you stick to the original formula, R equals to R equals to rho 4L over pi d square. Okay, and then you use this and form the fractional equation. So I have delta R over R equals to delta rho over rho plus 2 delta d over d plus delta L over L. And then I rearrange this, I get delta rho over rho equals to this, and then I have subtraction. Now this is fundamentally totally wrong because errors can never be subtracted. So that is the reason why you must express the equation, rearrange the equation such a way that it has to be based on the subject of the formula. Okay, the thing you want to, your final answer, the quantity which is your final answer must be the subject of the formula. Because if you don't do that, you end up having subtraction in your formula, which is wrong in your equation. So error cannot have any subtraction. Okay. Okay, the second one is a bit self-explanatory, but this is very important. Every time students miss out on this. Explain what the new resistance of the wire would be if it stretched uniformly to twice its original length. Okay, just remember, if you stretch it to twice the original length, the area is half, because when you stretch something, the volume is the same. Okay, the volume is the same. And if volume the same, the length is twice, the area is half, so therefore the volume is now a quarter. Okay, no, sorry, the volume is not, the volume is the same. The resistance is now 4 times the original value. Okay, so it's all here. When the length is twice the original length, the cross-section area is now half. Okay, resistance equals to rho L over A. Okay, this one you learn in secondary school, but we'll learn this more in the electricity chapter later. So remember, when you stretch it, if the length is double, the area will be halved. So double divided by half equals to 4 times. So the resistance is now 4 times the original value. Okay. But yeah, this is just an awareness part. You'll find this more useful next time when you study electricity, because but then again, this concept is often asked when you study electricity chapter. Okay, so we will end the lecture here. This is the second of 3 lectures, so we'll continue with the third one later. Have a good day.